Hi, my name is Phương Nguyen. Today I will talk about our recent work in photo-induced anomalous Hall effect in 2D transition metal dichalcogenide. I performed this work during my time as an undergraduate student at the University of Alabama, Tuscaloosa, under Dr. Wang Kong-se. 2DTMDs are atomically thin semiconductors with direct band gap at the K and K prime point in the prevalent zone. The lack of inverse symmetry and strong spin-orbit coupling effect give rise to giant spin splitting in the conduction bands and valence bands of the material, as well as coupling the spin and valley degree of freedom. If we were to introduce a circularly polarized light and break time reversal symmetry, a net valley polarization can be created, which under a DC electric field, a measurable Hall voltage can be recorded. In this talk, we develop a theory for such a valley Hall effect. Our approach starts with the unperturbed massive Dirac Hamiltonian. We introduce the effect of circularly polarized light as a light-matter coupling term, which is treated non-perturbatively, allowing for strong optical pump as opposed to the weak linear response regime. The DC field is taken to be a weak perturbation to our total Hamiltonian. With excitation near resonance, we employ the rotating wave approximation and transform into the rotating frame where the calculation can be done more conveniently. In the rotating frame, we calculate the density matrix solution with two components. The zero order component is the response to the strong pump field, and the perturbation term rho with 1 is the correction to the zero order term up to first order in DCE field. After obtaining rho, we can transform back into the lab frame where the current and conductivity can be calculated by taking the trace of rho 1 with the current operator. The original Hamiltonian of TMD is taken to be the well-known massive Dirac Hamiltonian with valley index tau, spin index Fc, and 2 delta as the bandgap. We can algebraically group terms together such that the Hamiltonian give 4 copies, one for each of the possible combination of spin and valley. From the following, we shall consider only one such copies for a single spin and valley. The final results can be summed over the spin and valley index after. The electric field and vector potential A are introduced in the standard way such that the mu equal plus minus 1 is the helicity index of right and left circular polarization. The momentum term is substituted by the Peier's substitution to obtain the full Hamiltonian, including the light-matter interaction. In the rotating frame, we proceed to diagonalize the full Hamiltonian and obtain the photon dress band dispersion as a function of momentum. We plot these band, conduction bands, and valence bands in the case where excitation is below the band gap. As the frequency increases to exceed the band gap, as plotted to the right, we observe a level repulsion effect where the two bands touch and reopen again a dynamical gap. The dynamical gap size scales linearly with the pump field AC strength. With AC field up to 20 megavolt per meter, a gap size of around 8 millielectron volt can be observed. After having the Hamiltonian, the density matrix can be solved from the quantum kinetic equation seen here in the lab frame, where IC is the collision integral, which we describe using the relaxation time approximation. The unitary transformation into the rotating frame allow us to drop the time-dependent term from the first equations. The density matrix again have two components. The zero order component is solution to the light-matter interaction, and the rho 1 component is the correction term due to the addition of DC field. The density matrix is recasted into this form from a set of transformed pseudo-spin bases, sigma alpha beta gamma, and the identity matrix. The two equations obtained in the rotating frame became a standard 2x2 matrix equations, which can be solved algebraically first for the rho 0, and then subsequently using rho 0 to obtain rho 1. We plot here our rho 0 solution. The plots show the population difference between the conduction band and the valence band, assuming at equilibrium that we have an empty conduction band and a fully occupied valence band. so their original population difference is -1. Under the strong pump field of 100 megavolt per meter, the plot to the left shows the population difference for frequencies smaller than the band gap. As you can see, not much population can be seen, and most of the excited electron is at the point where k equals 0. In the plot to the right, when frequency exceeded the band gap, significant population of electrons fill the conduction bands near the dynamical gap plotted in the band dispersion before. The two plots here show the correction from row 1 first order density matrix to the previous population difference of row 0, again plotted for the two cases for below and above gap excitation. The DC field was chosen to be 10 kV per meter, which is much smaller than the AC field strength, still at 100 megavolt per meter. Again, only in the right plot where a significant population changes can be seen for frequency exceeding the band gap. The current responses can be calculated from the lab frame after we transform first order density matrix row 1 back from the rotating frame. We're taking the trace of row 1 with the single electron current operator, which we obtain by taking the vector derivative with respect to momentum from the HR. HR is the Hamiltonian after rotating wave approximation transformed back from the rotating frame. The unitary transformation operator U used here is the same as the one we used before when we go from the lab frame to the rotating frame to solve the density matrix. Our final result is the plot of photovoltaic Hall conductivity and longitudinal conductivity sigma xx and sigma yx by taking the current divided by the DC electric field. The three columns show the contribution from the two valleys and the final total conductivity. In each valley, we sum over the contribution from the two electron spin and observe the resonant feature near the interband transition of each spin. The numerical value of the two transitions are taken around to be 1.6 to 1.7 electron volt. For the choice of mu equal to 1 for right circularly polarized light, the contribution from the K valley conductivity dominated per selection rule, while the K prime valley is suppressed. And the magnitude of conductivity also increased with increasing pump strength from 10 to 40 megavolt per meter, as seen in the four different color plots here. Not shown here, however, as a quick sanity check, if we were to flip helicity of light from mu equal to 1 to mu equal to -1, the profile between K and K prime valley for Hall conductivity switch, as well as the sign of them switch from positive to negative. For the longitudinal, the profile for the K and K prime valley also switch, but the magnitude and the sign remain unchanged because the DC field does not change direction. This obeys time reversal rule. In conclusion, we have developed a theory for Valley Hall effect in 2D TMD using the density matrix formalism and rotating wave approximation. We obtain longitudinal and Hall conductivity in this system. For excitation frequency exceeding the band gap, a level repulsion effect can be observed in the band dispersion where a dynamical gap opens and scale linearly in gap size with the strength of the AC pump field. We also obtain strong resonant feature at the two-spin resolved band edge transition energy. Our work was supported by the Department of Energy, Office of Science, Basic Energy Science, and the University of Alabama. Thank you for listening.